So we'll start binomial function. Did I say function? Binomial expansions, not functions. The binomial theorem. So when you are studying this whole thing here, this thing can be summarized to a point where you understand that you're just dealing with a few things. If not 4, then there are 5. The first key thing is knowing how to expand A plus B to any power. Now, this has been a trick question, but people came in to make work easy. They started in a very simple way. They said, okay, what could be A plus B to the power 0? Since we know that n number to power 0 is 1, and they put 1 as a pivot, and then said, okay, what could be A plus B to power 1? Whenever you have power 1, you just get whatever is inside. So now to understand the pattern of the pivots there, I said, okay, instead of picking A plus B, instead of picking A and B, what if somebody used X plus Y? What if I use P plus Q? So let us just picking the coefficients of these variables. So in this case, we pick the coefficient of A and of B. Then you come back again and say, what if we add A plus B squared? This just gives us A squared plus 2AB plus B squared. So if you pick the coefficients again, you have 1, 2, 1. Now a nice observation here is starting to emerge. You can see that 1 plus 1, if we added just these 2, would have gotten these 2 here. Okay, but wait, maybe it was just a coincidence there. Let's do A plus B to the power 3. This is A plus B squared multiplied by A plus B. If you expand, the A plus B squared is A squared plus 2AB plus B squared. Now we multiply this whole thing by A plus B. A squared times A, we get A3, plus A squared times B, we get A squared B, plus 2AB times A, we get 2A squared B, plus 2AB times B, we get 2AB squared, plus B squared times A, we get AB squared, plus B squared times B, we get B3. So we have A3, this is just alone, but A squared B plus 2A squared B we can add and get 3A squared B, plus 2A squared plus AB, 2AB squared plus AB squared, we're getting 3AB squared, and then plus B3. So again, if we just go for the coefficients, we'll have 1, and then 3, and then 3, and then 1. It seems like now, if we added these 2 just, would have gotten a 3. You add those 2, would have gotten a 3. This means that in our next line, we know it's supposed to be A plus B power 4. So what we'll do now is that we won't do the expansion. We'll just come and add. So we'll have 1 plus 3. So if we add this, we'll get 4. 3 plus 3, we'll get 6. 3 plus 1, we'll get 4. And then put a 1 that side. If we wanted to understand what A plus B power 5 could be, we'll just come back to the triangle here and say 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, and another one that side. Now the guy who was trying to start this named this thing after himself, and we call it the Pascal's triangle. So it helps us to get the coefficients of the expansion. Now we go back and see how we're going to be getting those coefficients. When it was a power 0, we just got 1. When it was a plus b power 1, we had 1 power 1 plus b power 1. There we could not understand anything when it comes to the powers. A plus b squared, we had a to the power 2, and the next thing a was to the power 1. And then b appeared to the power 1, then b increased the power to 2. You go to the third one, you get a power 3, a power 2, a power 1, and a power 0 in the last one, meaning that the powers of a are decreasing. It was 3, it became 2, it became 1, until it went to 0. The powers of b, we had 0, then increased, we had 0, then increased to 1, increased to 2, increased to 3. So the powers of a are going down as the powers of b are going up. So this would mean that if we are to bring the whole expansion of a plus b power 4, since we know the coefficients are here, then we would say, okay, that one is just a power 4 plus the coefficient is 4. So a should reduce a power to lose 1 power, give it to b. And then we'll have 6. A will lose another power, give it to b. Then we'll have 4. A will lose 1 more power, give it to b. And then b will take all the powers. Let's go to 5. We would say a5 plus 5 a4b plus 10 a3 b2 plus 5 a2. Or there are 2 10s. So plus 10 a2.
So,
Hello?
so start from where you're saying the powers of A are decreasing and the power of B are increasing. I didn't get that part.
Okay, so let's get it now in here. What do we mean by the powers of A going down and the powers of B going up? Okay, so following up the patterns here, if you look at how A plus B power 3 is, we did the actual expansion and got this. So we had A power 3, A power 2, A power 1, A power 0, that's why there's no A here. B power 0, that's why there's no B here. B power 1, B power 2, B power 3. So the powers are switching. As the powers of A decreases, the powers of B are picking up. That's the reason why when we go to 4, we would give 4, we would give A 4. In the next position, A will have 3 as B picks the last one. And then A will have 2, B will also have 2 now. A will have 1, B will have 3. And then B will have all the powers. So that if we go to power 5, we'll have A 5 plus 5 A 4, B will appear now, plus 10 A 3 B 2, plus 10 A 2 B 3, plus 5 A B 4, plus B 5. So if we increased, if we wanted to get A plus B power 6, we could easily say, okay, first we go and get the coefficients. So I'll put it in blue. 1 here, then we add, we'll get 6. We add, we'll get 15. We add, we'll get 20. Add 15, add 6, and then 1. We get now those, we'll bring them down here. So we'll have A6 plus 6, A5, B, plus 15, A4, B2, plus 20, A3, B3, plus 15, A2, B4, plus 6A, B5, plus B6. So this now, we're getting all this information from the Pascal's triangle, okay? Now what happens if the numbers become so big? Suppose we have A plus B to the power 15 or to the power 10, and your handwriting is big. It will require that you should go to another page, listing all this. So now, this guy, Isaac Newton.
Sir,
Hello?
the other board just on the last part is blue.
Hello?
So I'm done.
6.
Okay. So now, since the work here looks like it can be involving if the powers become big, Isaac Newton now came in and said, okay, instead of you guys having a lot of sheets to put the coefficients, why can't you just drive the method of having those coefficients there? Okay, suppose we call this thing A plus B to the power n. Instead of saying 1, you just say n to 0. And then, since you are giving the whole n to A in the first position, still give the whole n to A. Plus, you reduce it a bit to n1, A, n minus 1, and then let B appear. Plus, n2, A, n minus 2, B2. Plus n3, A, n minus 3, B3. So you keep going so that if you get a general term where you don't know what that error is there, just treat it the same way you treat the numbers that you know, subtract it from n and give it to B. Keep going until you get to the last one where there will be nn, and then A won't appear, only B will appear with all the powers. And we are calling this the binomial theorem. So this is the actual binomial theorem. So you can see that the work now is becoming easy. We can do any expansion even if the power is 15 without having more things right on the paper. But what could n to 0 be then? Since it has appeared here and you are saying it must give us the same coefficients just like the Pascal's triangle. So we need to have a proper definition of n. So let's define the general case. N choose R as n factorial, R factorial, and then n minus R factorial. Okay. Then from there, now this definition holds when n is greater than R. Okay. What we call n factorial is just the product of n by the smaller number. You're just reducing by 1, reduce by 1 again, reduce by 1, keep reducing by 1, all the way until you get to n minus n, then you put a factorial. Now you understand that n minus n will just be 0. So the last number should be 0 factorial. Now, if 0 factorial is allowed to be anything else, it can make this whole thing useless, if not funny. So what we'll do is we'll have to define it as 1 so that our expansion makes sense. Because imagine coming from 100 by 99, by 98, by 97, 96, you get to 0 factorial, it becomes 0, meaning the whole thing you have done here is just 0. So now to avoid that, 0 factorial was defined as 1. So that if you can have nice examples of the factorials, if we have evaluate a 3, choose 1, we will get 3 factorial. Since 3 is our n now, 1 factorial, our r, 3 minus 1 factorial, giving us 3 factorial over 1 factorial. 3 minus 1 is 2 factorial. Now, since we are allowed to reduce 3 by the definition of factorial, this is 3 by 2 by 1 by 0 factorial. Down, we have 1 by 0 factorial, 2 by 1 by 0 factorial. So now in mathematics, we know that if we are multiplying and some things are common, you can just cancel them out. Cancel them out. And then you remain with 3 by 1 by 1 by 1, which is just 3. 1 by 0 factorial is just 1, giving us 3. So if somebody just said, instead of me doing this, which cancels there, why can't I just be saying 3 by 2 factorial over 1 by 0 factorial by 2 factorial, so that at this point I cancel that with that and remain with 3 over 1, which is equal to 3. This may help if the numbers are too big. Let's see. 11, choose 9. This is 11 factorial over 9 factorial, 11 minus 9 factorial. This is 11 factorial over 9 factorial, 11 minus 9, that's 2 factorial. Now, if you don't want to be doing this, what will happen is that you have to say 11 by 10 by 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 by 1 by 0 factorial over, you come down and say 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 by 1 by 0 factorial multiplied by 2 by 1 by 0 factorial. And then you get back and start canceling. This 0, that's 0. This 1, that 1. 2, this 2. 3, that 3. 4, 4. 5, 5. 6, 6. 7, 7. 8, takes our 8. 9, takes our 9. And then that's when now you have 11 by 10, 110 over 2 by 1, 2. You divide there, you get 55. You understand that would have wasted a lot of time. And then another guy say, why should I repeat all that? Let me just go all the way up to 9 factorial up, since I have a 9 factorial down, and just expand the 2. So that I cancel this, cancel that, and then get 110 over 2, giving me 55. Same answer, but the other one wastes time, then the other one goes in the shortcut. So what we'll be doing is from there, we'll be coming direct to this one. because we understand now what we are avoiding. Okay. This means that if we went back now to the binomial theorem and recalculate these coefficients there, we may come up with an easier way of using that binomial theorem. So now, what we'll do is, since we said the theorem is A plus B for n, giving us n0, an, n1, an minus 1, b.
So can you scroll back to the adjustment?
An minus 2b2, n3, an minus 3b3, nr, an minus rbr, all the way up nn, bn. Okay, so now, since we know how to, since we have defined nr as n factorial, r factorial, n minus r factorial, let's see what n0 would give us. This would be n factorial over 0 factorial, n minus 0 factorial, which is n factorial, 0 factorial, n factorial. Now n and n can cancel, so we'll have 1 over 0 factorial is 1, so we get 1. So next time we see n to 0, it will be the same as we have seen 1.
Basa,
You know?
Basa mlipast.
Oh.
So you're fast.
Okay, I'll be slow.
Sapitano Moncalas, sir.
Where?
Into 0.
Ah. Okay. By definition, n to 0, n is still in the position of n in nr, then r has become 0. So you're substituting. Where there's r here, you put 0. Where there's r, you put 0. Then what is the, then we say 0 factorial is what? Is 1. So 0 factorial is 1. What is n minus 0? It's just n. So you have n factorial over n factorial. The numbers are equal. So we get 1 over 1, giving us 1. So that if you do n choose 1,
Sir,
you know?
so this factorial, the main sense is to find the coefficient. Isn't it the same?
Yeah, it's the same thing. These factorials came in to take the place of the Pascal triangle.
Right.
Okay. So n choose 1, we just replace n is still n, r has become 1, and then n minus r, it will be n minus 1, meaning n factorial. Now 1 factorial is just 1, so we have n minus 1 factorial down. Now we understand that calculating this, we need to reduce the top one all the way up to 0. So we start n multiplied by n minus 1 factorial. We end at n minus 1 because we discover that down here we have it. So we are avoiding this thing of canceling. So once we discover that what we have written on top there, we have it down, we pause there and see if those two can cancel. And for sure, n minus 1 factorial is just the same as n minus 1 factorial. So that that piece just gives us n. So n choose 1
So can you just,
has come out to be n.
sir,
You know?
can you just explain this example here? The second one, the one about one.
The n choose 1. The n choose 1.
Yeah.
Okay. James?
Yes, sir. How have you done it there? N minus 1, n minus 1. There when how have you arrived to n minus 1 factor?
Okay. So we are saying when it is n choose 1, this is the same as n factorial over 1 factorial, the R, and then n minus 1 factorial. Now, how have we defined n factorial? We said you can keep multiplying going down all the way up to 0. Okay, which we have seen that if we wanted with this one here, you could go all the way down up to 0 factorial, come down, get this, take it all the way down up to 0 factorial. But then there will be much work of canceling. So what we'll do when we get here is that we're supposed to, since n is defined as n minus 1, n minus 2, going all the way down, we're supposed to start doing that, n minus 1, and keep going. But in the denominator, we have n minus 1 factorial. When we reach 9 factorial on top here, we say it will be better to stop here since we have 9 factorial. In mathematics, if you are dividing a by itself, even if no one has told you what a is, you will know that this is 1, that is 1 giving you 1. This means that even if I don't know what n is, for as long as I have n minus 1 factorial over n minus 1 factorial, then these will cancel each other, or this one in itself 1, that one in itself 1. So what we have now is n multiplied by 1 over 1 giving us n, even if the n is unknown. So you do n choose 2, you have n factorial over 2 factorial n minus 2 factorial. This means that you get the numerator n, reduce it to n minus 1, go to n minus 2, end there because there is an n minus 2 in the denominator. So we have 2 factorial and the n minus 2 in the denominator. Since we know that mathematically n minus 2 factorial is the same as n minus 2 factorial, so these two will help us not go very far, so that we remain with n multiplied by n minus 1 over 2 factorial. If we went to n choose 3, you discover that we have n factorial on top, 3 factorial, n minus 3 factorial. That is n minus 1, n minus 2, n minus 3. We're supposed to keep going, but we have identified, we've seen that there is 3 factorial and n minus 3 factorial. So if we went, everything that comes after n minus 3 will also be down. So this means that n minus 3 factorial will take away n minus 3 factorial. So we'll have n multiplied by n minus 1 multiplied by n minus 2 divided by 3 factorial. So this means that if we went back, so far we know what this is, we know what this is, we know what that is, we also know what this is. So we have a plus b to the power n is equal to, where there is n to 0, we say it is just 1. So 1 times an, we just get an, plus where there is n choose 1, it's just n. So it will be n, an minus 1, b, plus where there is n choose 2, we said it is just this. So we have n minus 1 over 2 factorial a n minus 2 b2 plus n choose 3 would be n minus 1 n minus 2 over 3 factorial a n minus 3 b3. So we can keep going. So we'll need these expansions in some application questions where you don't have to go that far, but you just end at power 3. So we'll see such type of questions and how they come about. So do we have questions here?
Excuse me, sir.
Sir, you are too fast and our heads are getting tired.
Eh. No, it's not that V. You're at physics. Which one?
After a, the power n plus.
After a to the power n plus n multiplied by a
Yes.
to the power n minus 1 b.
Oh, all right, right.
Sir,
Hello?
here where there's n sunshine 0, that one.
N choose 0.
Can't it be n factorial only if we were to multiply the n times the 0 outside? Oh, okay, it's fine.
All right. So this topic is not that complex. So in the next 1 hour, I can finish this whole topic. But since you are tired, we'll end here.
No, don't finish it, sir. Let's just take it slow, sir.
Okay, I'll take it slow. So today, this is enough. So go through just these three pages. 1, 2, 3. And then we might have a class per weekend that will negotiate there so that we can finish. Finish
So,
this. Yeah?
Okay, I just joined with you this same month, and then so is it that we are just revising, or that's when we are?
No, we're assuming that we have never learned this thing. So this is our first day doing binomial. And so we'll do every part of binomial.
Okay, thank you.
And
So
the
with
next
this
topic.
space we are okay. We can finish the syllabus before November.
Yeah. We're just doing a few topics. This is topic 3. We've done sets, we've done functions. We're now on binomial.
Okay.
Then we'll go
But
to
our pace is okay.
we're even too fast.
Okay, okay. Thank you.
Don't worry.
So how many topics are we supposed to get done with?
How many are remaining? We have trig, logs and exponential, calculus. Then for the guys doing 1120, you have probability and statistics. So only 4 topics to go. And then the other guys, when you reach calculus, you start doing induction, matrices.
So for those who have calculus, they are not supposed to do matrices.
Anyway, depending on how they will tailor your course, there might be no in both courses. There's calculus. Now in the other course, there may not be matrices because of probability and statistics.
Oh yeah, I meant matrices and probability.
Yeah. So
So
there
I
you
paid
part
them
ways. Okay, so and don't worry about the pace. It's very